Welcome to Multivariable Calculus. For 15 episodes, we lived on a number line. Functions took one number in, gave one number out. Their graphs were curves in a plane, derivatives were slopes of those curves, integrals were signed areas underneath. Beautiful subject, thoroughly explored. Today the curtain lifts on a much bigger theater. The input is no longer a single number, it's a point in space. A pair xy, a triple xyz, or in general an n-tuple of real numbers. And the graph of a function of two variables, z equals f of xy, is no longer a curve. It's a surface floating in three-dimensional space. Almost every concept we worked out in one-variable calculus has a multivariable analog. Derivatives become partial derivatives, and then gradients. Integrals become double and triple integrals. The fundamental theorem generalizes into Green's, Stokes's, and the divergence theorem. But before any of that, we need the geometry. The 3D coordinate system. The distance formula. Spheres. The trick for visualizing surfaces by collapsing them to topographic maps, and the two alternative coordinate systems, cylindrical and spherical, that physicists reach for whenever a problem has symmetry. That's today. Let's get the setup straight. In one-variable calculus, a function f maps the real numbers to the real numbers, one number in, one number out. In multivariable calculus, the general object is a function f from n-dimensional space to m-dimensional space. The input is an n-tuple of real numbers. The output is an m-tuple. Two special cases dominate practice. First, scalar-valued multivariable functions. F maps n-dimensional space to the real numbers. The output is just one number. This is the most common case. Two variables, f of x, y, think elevation over a map or potential in a plane. Three variables, f of x, y, z, think temperature at every point of a room or pressure throughout the atmosphere. Second, vector-valued functions. F maps n-dimensional space to m-dimensional space with m at least 2. The output is a vector, a velocity field in fluid dynamics, a parameterization of a curve or surface, the derivative map that turns a function into its Jacobian. We'll meet those starting in a few episodes. For today, we focus on the most common case. N is 2 or 3, and the output is a single number. The graph of z equals f of xy is a surface living above the xy plane. That object, a surface in three-dimensional space, is what we need the geometry to handle. Time to build the stage. The three-dimensional coordinate system uses three mutually perpendicular axes through a common origin. The convention almost everyone uses, x-axis pointing out towards you, y-axis pointing to the right, z-axis pointing up. Three numbers, x, y, z, specify a unique point. Here's a subtle point that matters. There are two inequivalent ways to orient three axes in space. They are mirror images of each other. To pick one consistently, we use the right-hand rule. Take your right hand, curl your fingers from the positive x-axis toward the positive y-axis. Your thumb points along the positive z-axis. That's a right-handed coordinate system, and it's standard everywhere in math and physics. The three coordinate planes are pairs of axes. The xy plane, where z equals 0, is the floor. The xz plane is y equals 0. The yz plane is x equals 0. They are mutually perpendicular and they intersect at the origin. Those three planes cut space into 8 regions called octants, the three-dimensional analog of the 4 quadrants in the plane. The first octant is the one where all three coordinates are positive. The others don't have universally agreed upon numbers, so people usually just describe them by the signs of x, y, z. Here it is. 3 perpendicular axes through the origin with the standard orientation. A sample point P at coordinates 2, 1.6, 2 sits up in the first octant, with dashed drops showing where it projects to the xy floor and to the x and y axes. The orange arrows annotate the right-hand rule. Curl your fingers from the positive x-axis around to the positive y-axis. That's the curling arrow in the floor. Your thumb points up along the positive z-axis. That's the straight arrow going upward. Every 3D picture in this series uses this same orientation. If you ever see someone else's figure where the curl goes the other way and the thumb points down, that's a left-handed system, and the cross products will all come out backward. We stick with right-handed. The distance formula in 3 dimensions is almost exactly the formula you already know from the plane, with one more squared term under the square root. The distance between the points x1, y1, z1, and x2, y2, z2 is the square root of the sum of 3 squared differences, one for each coordinate. Why does this work? Apply Pythagoras twice. First, in the floor, the horizontal separation between the projections of the 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared. That's the regular 2D formula. Then combine that horizontal distance with the vertical gap z2 minus z1 using Pythagoras again. They form a right triangle with the true 3D distance as the hypotenuse. Square the horizontal distance, add z2 minus z1 squared square root. Out popped the 3-term formula. The same logic works in any number of dimensions. In n-dimensional space, the distance between 2 points is the square root of the sum of n-squared coordinate differences. Pythagoras was generous, it generalizes for free. The equation of a sphere is then just the distance formula set equal to a constant. The sphere centered at A, B, C with radius r is the set of points x, y, z satisfying x minus a squared plus y minus b squared plus c minus c squared equals r squared. The unit sphere centers at the origin with radius 1, x squared plus y squared plus z squared equals 1. It will show up roughly forever. Pattern recognition: in 2D, the circle is x minus a squared plus y minus b squared equals r squared. In 3D, the sphere adds z minus c squared. In n dimensions, the hypersphere just keeps adding squared terms. The graph of a one-variable function, y equals f of x, is a curve, a one-dimensional object living in the two-dimensional xy plane. The graph of a two-variable function, z equals f of x, y is the natural analog, a two-dimensional object living in the three-dimensional xyz space. We call it a surface. Specifically, it's the set of all points x, y, z such that z equals f evaluated at xy. For every input point in the floor, you go up by f of xy units. The result is a sheet hovering above and below the xy plane. 4 examples to get a feel. The graph of z equals x squared plus y squared is a paraboloid, a bowl opening upward. The graph of z equals x squared minus y squared is a saddle, also called a hyperbolic paraboloid, that goes up in one direction and down in the perpendicular direction. The graph of z equals the square root of 1 minus x squared minus y squared is the upper hemisphere of the unit sphere. And z equals sine x times cosine y is a rippled surface that looks like an egg carton. What about functions of 3 variables? The graph of w equals f of x, y, z would live in 4-dimensional space which we can't draw. That's where the next idea, level surfaces, becomes essential. Here's the paraboloid z equals x squared plus y squared as a surface in 3D. The blue grid shows the sheet itself. The orange circles on the floor are the projections of horizontal cross-sections at various heights, and the vertex at the origin sits at the bottom of the bowl. The whole shape is rotationally symmetric around the z-axis. Now look at those orange circles. They are the curves you'd see if you sliced the paraboloid horizontally, at height z equals ce, and then projected the resulting cross-section down to the floor. Each slice is a circle of radius, the square root of c. Larger c, bigger circle. Smaller c, smaller circle. At c equals 0, the slice shrinks to a single point, the vertex. Those circles on the floor are called the level curves of f. They are a 2D stand-in for the 3D surface, and they are the most useful tool for visualizing surfaces by hand. Next slide. Here's the central visualization trick of multivariable calculus. The graph of z equals f of xy lives in 3 dimensions. You can try to draw it, but the result is often cluttered. Instead, pick a value c and look at the set of input points xy where f of xy equals c. That set is a curve in the xy plane, called the level curve at level c. Geometrically, the level curve is what you get by slicing the surface with the horizontal plane z equals c, and then projecting the slice down to the floor. Walk along the level curve L sub c, and the function f is constant. You have seen this construction your whole life. Every hiking map ever made is a plot of level curves of the elevation function over the map's region. Where the contour lines bunch close together, the slope is steep. The function changes a lot over a small horizontal distance. Where the lines spread apart, the slope is gentle. Closed loops mark peaks and basins. Figure 8 crossings mark saddle points. Topographic maps are level curve plots, and they encode the whole shape of the underlying surface in 2 dimensions. For functions of 3 variables, the same trick works 1 dimension up. Set f of x, y, z equal to c, and you get a surface, called a level surface, inside 3D space. For instance, the level surfaces of f of x, y, z equals x squared plus y squared plus z squared are concentric spheres of radius, the square root of c. Level surfaces are the standard way to visualize functions of 3 variables, since their graphs would require 4 dimensions to draw. First worked example, sketch the level curves of f of xy equals x squared plus y squared. Set f equal to a constant c, and we get x squared plus y squared equals c. 3 cases. If c is negative, no point x, y satisfies the equation, because squared real numbers can't sum to a negative number. The level set is empty. If c equals 0, the only solution is x equals y equals 0, a single point at the origin. If c is positive, x squared plus y squared equals c is the equation of a circle of radius, the square root of c centered at the origin. So the level curves are concentric circles around the origin, with radii growing like the square root of c. At c equals 1, radius 1. At c equals 4, radius 2. At c equals 9, radius 3. At c equals 16, radius 4. Notice an important pattern. If we pick the level values c equals 1, 4, 9, 16, spaced by 3, 5, 7, growing apart, the radii come out evenly spaced at 1, 2, 3, 4. But if we instead space the levels evenly as c equals 1, 2, 3, 4, 5, the radii are 1, the square root of 2, the square root of 3, the square root of 4, the square root of 5, which compress as c grows. The circles bunch up the higher you go. Topographically, that's saying the paraboloid gets steeper as you walk outward, which matches the picture of a bowl whose walls keep getting more vertical. Second worked example. The level curves of f of x, y equals x squared minus y squared. Set the function equal to c, x squared minus y squared equals c. This is the equation of a hyperbola. Three regimes. If c is positive, the hyperbola opens left-right. The branches cross the x-axis at plus or minus the square root of c, and the asymptotes are the diagonal lines y equals plus or minus x. As c grows, the vertices move farther from the origin along the x-axis. If c is negative, the hyperbola opens up-down. The branches cross the y-axis at plus or minus the square root of the absolute value of c. Same diagonal asymptotes. And c equals 0 is the magic level. The equation becomes x squared equals y squared, which factors as x minus y times x plus y equals 0, giving the two lines y equals x and y equals negative x. The level curves collapse from hyperbolas to a pair of crossing diagonal lines. That's the degenerate level. Geometrically, the surface z equals x squared minus y squared is a saddle, also called a hyperbolic paraboloid. Walk along the x-axis with y equals 0, and the surface curves upward like a parabola. Walk along the y-axis with x equals 0, and the surface curves downward, also like a parabola. At the origin, the point 0, 0, 0, the surface has a saddle point, a critical point that is neither a maximum nor a minimum. The diagonal lines at level 0 are the level set passing exactly through this saddle. We'll meet saddle points formally when we study optimization in episode 9. For now, just notice how much the level curve plot tells us about the shape of the surface. Third worked example, deliberately picked to be a little different. Sketch the level curves of f of x, y equals y minus x squared. Set f equal to c, and solve for y, we get y equals x squared plus c. For each constant c, the level curve is a parabola in the xy plane, the standard upward opening parabola y equals x squared, shifted vertically by c units. At c equals 0, we get y equals x squared. At c equals 1, the same parabola shifted up by 1. At c equals negative 1, shifted down. The whole family is a stack of identical vertically translated parabolas. This is a useful counterpoint to the previous two examples. The level curves of x squared plus y squared were concentric circles. The level curves of x squared minus y squared were hyperbolas with degenerate diagonal lines. Both families had the origin as a special point. Here, with y minus x squared, the level curves are an infinite translation family. There is no special center, no degeneration, just a stack of parallel parabolas. Geometrically, the surface C equals y minus x squared is a parabolic cylinder tilted in 3D. At every fixed x, the surface is linear and y by a subit, z equals y minus a constant, a slanted line. At every fixed y, the surface is the downward parabola zb equals negative x squared plus a constant. The takeaway, level curve plots come in all shapes: concentric circles, hyperbolas, ellipses, translated parabolas, spirals, whatever. They are the universal 2D projection of a 3D surface. Two level curve plots side by side. On the left, x squared plus y squared equals c for 4 positive values, concentric circles around the origin. The bigger c gets, the larger the radius. Simple, symmetric, rotationally invariant. On the right, x squared minus y squared equals c across positive, negative, and 0 levels. The blue curves, positive c, are hyperbolas opening left and right, with vertices on the x-axis. The orange curves, negative c, are hyperbolas opening up and down, with vertices on the y-axis. The two red diagonal lines are the level set at c equals 0, the asymptotes that both families approach. Notice how the hyperbolas rotate by 90 degrees as c crosses 0. That qualitative change in the level curve geometry is the signature of a saddle point at the origin of the surface z equals x squared minus y squared. Pictures like this are the working tool of multivariable calculus. When you can't visualize a surface directly, you draw the level curves and read the surface's shape off the topographic map. A quick preview of two alternative coordinate systems we'll deploy heavily starting around episode 13. Cylindrical coordinates are polar coordinates in the xy plane with the z-coordinate untouched. To convert, x equals r cosine theta, y equals r sine theta, and z stays as is. The radius r is the horizontal distance from the z-axis, the angle theta wraps around in the floor, and z measures the height as before. Use cylindrical whenever your problem has rotational symmetry about the z-axis. Pipes. Rotating disks. The flow of water through a circular channel. The magnetic field around an infinite straight wire. In all these, the function or field depends mostly on r and z, not on the azimuthal angle theta, and writing it in cylindrical coordinates collapses two variables into one. Spherical coordinates use the distance from the origin ρ, a polar angle phi measured from the positive z-axis downward, and an azimuthal angle theta measured around the z-axis. The conversion formulas are x equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi. The convention here is the standard one in math. Physicists sometimes swap phi and theta, so watch out when crossing textbooks. Use spherical whenever your problem has spherical symmetry about the origin. Planets, atoms, gravity from a point mass, the electric field from a point charge, the volume of a ball. The trick everywhere is match the coordinate system to the symmetry of the problem, and ugly integrals become beautiful. So why do we care? Because multivariable functions are how the real world is described. In physics, every potential is a function of position. The gravitational potential of a point mass is b of x, y, z equals negative gm over the distance from the mass, which uses the 3D distance formula we just derived. The electric potential around a charge distribution is a function of all three spatial coordinates. If the problem depends on time too, like the temperature in a room that's heating up, you get a function of four variables, t of x, y, z, t3 spatial plus 1 temporal. The heat equation that governs that function is itself a statement about partial derivatives, which we'll meet in episode 4. In economics, the utility u of x, y that a consumer assigns to a bundle of x units of one good and y units of another is a function of two variables. Its level curves are called indifference curves, bundles the consumer is indifferent between. The production function P of k, L, relating output to capital and labor is similar. Its level curves are called isoquants, sets of input combinations producing the same output. All of microeconomics runs on multivariable calculus. In engineering, stress and strain are tensor fields over a loaded part. The drag on an aircraft depends on a dozen design parameters, and any non-trivial optimization happens in multivariable input space. The thing being optimized is a multivariable function. The gradient tells you where to step. The Hessian tells you whether you found a maximum, minimum, or saddle. None of this is exotic. It is the mathematics that makes modern science and engineering work. We're at episode 1 of that. Recap. Multivariable calculus studies functions f from n-dimensional space to the real numbers or to m-dimensional space. We will spend most of our time on two variable scalar functions f of x, y, and 3. Variable scalar functions f of x, y, z. Three-dimensional space is built from three mutually perpendicular axes through the origin, oriented by the right-hand rule, curl from x to y, thumb points along z. The three coordinate planes divide space into 8 octants. The distance formula is Pythagoras with one more squared term. Distance squared equals delta x squared plus delta y squared plus delta z squared. The equation of a sphere of radius r centered at a, b, c is x minus a squared plus y minus b squared plus z minus c squared equals r squared. Pattern, each dimension adds one more squared term. The graph of z equals f of x, y is a surface in 3D. We can't draw the graph of f of x, y, z directly, it would live in 4D, but we can visualize either kind of function by collapsing it to a topographic map, the level curves f of x, y equals c for a 2-variable function, or the level surfaces f of x, y, z equals c for a 3-variable one. 3 sketched examples. X squared plus y squared, concentric circles around the origin, radius the square root of c, surface is a paraboloid. X squared minus y squared, hyperbolas opening one way for positive c, the other way for negative c, with diagonal lines y equals plus or minus x at the degenerate level c equals 0, surface is a saddle. Y minus x squared, vertically translated parabolas, surface is a parabolic cylinder. Cylindrical and spherical coordinates are symmetry-friendly alternatives to Cartesian. Cylindrical for rotational symmetry around the z-axis, spherical for symmetry around the origin. We'll use both heavily in integration. And multivariable functions are everywhere: potentials in physics, utilities in economics, temperature fields, and stress tensors in engineering. Next episode, we add the algebra, vectors, the dot product, the cross product, the tools for actually moving around in three-dimensional space. That's the geometric foundation of multivariable calculus. Functions are now maps from n-dimensional space to the real numbers. Graphs are surfaces. Surfaces project to topographic maps via their level curves. Three-dimensional space has the right-hand orientation, the Pythagorean distance, and the sphere equation. Cylindrical and spherical coordinates are waiting for when we want them. If this helped, like, subscribe, drop a comment. Sketch the level curves of a function you find interesting: a product xy, a ratio x over y, an exponential e to the x plus y, anything, and post the result. The level curve picture is one of the most useful 2D summaries of a 3D surface, and the patterns that show up are surprising more often than not. Next episode, we install the algebraic machinery, vectors as displacements in space, the dot product, which measures lengths and angles, the cross product, the strange operation that only exists in 3 dimensions and produces a vector perpendicular to 2 others. Once we have those, we can talk about lines, planes, projections, areas, and volumes, the whole geometry of 3D algebraically. See you there. Today, we built the stage. Functions of several variables are maps from r to the n to r or r to the m, and their graphs live in higher dimensional space. The 3D coordinate system uses 3 mutually perpendicular axes, oriented by the right-hand rule, dividing space into 8 octants. The distance formula generalizes Pythagoras one extra term at a time. The sphere x minus a squared plus y minus b squared plus c minus c squared equals r squared is the natural analog of the circle. The graph of z equals f of xy is a surface in 3D, and we project that surface to a 2D topographic map by taking level curves f of xy equals c. We sketched 3 examples: the paraboloid's concentric circles, the saddle's hyperbolas with diagonal lines at level 0, and the parabolic cylinder's translated parabolas. Cylindrical and spherical coordinates are alternatives to Cartesian, useful when the problem itself has symmetry, cylindrical for pipes and rotating disks, spherical for planets and electrons. Multivariable functions are everywhere. Physics writes potentials, v of x, y, z. Economists write utilities, u of x, y. Engineers write temperature fields, t of x, y, z, t. Next episode, we install the algebraic machinery for moving around in 3D space. Vectors, the dot product, the cross product. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.